All right. Sorry, I got cut off last time, but let's see if we can just tie this up. Um, this will be short, hopefully. But last time we were talking, we were about to finish up this rate law. Um, so I just finished writing that out. So this would be our final rate law for that equation, for that mechanism. The next question is asking about the observed rate law constant. So that's our K is what we're talking about right there. And like I tried to mention, the K that we have here, or like actual K, our K observed, is composed of the Ks from all those different steps in the mechanisms. So if you were ever asked to have an expression, this is when keeping track of those guys would be valuable. So, and for like if you want to just pretend they're all 1K, like you can equate those in your minds. But if you want to write an actual expression, it would be related to the Ks from all of those steps. So that would be our K, like what is our K composed of? We've already like kind of talked about this, but let's just kind of make sure we're all on the same page. How do you use a reaction profile to represent a multi-step mechanism? So first of all, let's kind of just look in at this mechanism. Let's write our overall just to kind of get that out of the way. I noticed this is an intermediate. I noticed this is a catalyst, meaning that my overall is this. And then I noticed that I have a slow and a fast step, and I have these two separate steps. So the thing about like showing it on a mechanism or on a reaction profile is just that it's going to be clear that you have those two steps. So if there's two steps, there's going to be 1, 2 bumps. If there were 3, there'd be 3 bumps, and so on. Like it's just showing those different things. So let's just kind of orient ourselves. So like on any reaction profile, the starting place is always going to be your reactants. And that's ending energy is going to be your products. Okay. And then you have this other flat part in the middle. That is where your intermediates energies are going to be represented. So we're representing the energy of our intermediates. Okay. And on top of the hill, that's called our transition state. I tend to call it a transition state. I've seen AP call it an activated complex more often. So just be comfortable with both words. And then our second bump, that is going to be our second transition state, our second activation energy. Okay. So this is the intermediate. That's our actual like thing we have created and are then going to immediately consume. These tops of the hills are representing a temporary place where like bonds have been starting to break and starting to form, but have not quite actually done so. So two different kind of things. And the real important thing that I see asked about most is one, being able to represent exo and endothermic. So like we've talked about a bit earlier when we talked about our reaction profiles, anything that is endothermic will have a gain of energy. So if this was endothermic, I'll just draw it in for a second just so you can see it. If this first step was endothermic, my spot would actually be over here because that would show that I have gained some energy. So being able to recognize endothermic means I'm going to gain energy versus right here, it's showing that this step is exothermic. Same with this step. You can notice we went from this energy to this energy. This is also a negative change. This is exothermic. Okay. And the other thing they like to ask about a lot is looking at our activation energy. So that, again, activation energy is from wherever you're starting at to the top of the hill. So for this one, it would be from here to up here. This whole change, that is your first activation energy. And then this one from your starting to the top of the hill would be your second activation energy. So for that first step and then for that second step. Notice that that first step, you can see it's a much bigger activation energy, much bigger hill to get over. So that first step has the higher activation energy, which makes sense. Let's look back at our activation. Let's look back at our mechanism. The first step is our slow step. So that makes sense, right? Like if it is a slow step, if it is less likely to happen, if it's taking longer to happen, it must be because there's a bigger threshold to get over, a bigger activation energy. So if you were given the mechanism, you'd know that you'd have to show the slow step with a large activation energy. And we already did this, but we can recognize that both are exo. Oh yeah, I'll also point out, so we could focus in on like one step at a time, which is kind of what I showed here, or we could focus on the reaction overall, which in this case, like they're all exo, but it could be different. Maybe you have one endo step, one where the energy has increased, but overall you still get a decrease in energy. So let me mark that on here. So from our reactant energy level, which would be here, to our product energy level, which would be here, that's our reaction change in energy, which would also be exo in this case because it's gone down. Okay. So just to point out that those are all things we could infer from this beautiful graph. And yeah, I think that's kind of it. Catalysts, I'll show you some, we'll talk a bit more about this one, like actually in class, I'll show you some visuals for it. But we'll just clarify, a catalyst always is meant to increase the rate of a reaction by providing an alternate pathway with a lower potential energy of the activated complex, aka a lower peak, aka a lower activation and energy. So that's the point of a catalyst. If we're designing an experiment to be catalyzed, to be sped up in this way, we would pick one which would have this effect. And they work in a few different ways, and I think I'll just save that for class, but that's kind of it. Yeah, see ya.